Going to share the screen. So camera, that's it. We're on. Okay. So good afternoon. Okay, what we are doing for this session is take a little bit of a break. Okay, and I want to take you back to the very first week of this module. Do you remember what we said about the assumptions of this method? What are some of the assumptions of this plastic theory? Do you remember? You may get them in the quiz. So what are the assumptions? Huh? Bilinear. Okay. The stress-strain distribution bilinear. What else?
The material is isotropic.
My material is homogeneous and isotropic. Yes.
Maximum stress assumed is yield stress.
The yield stress is the maximum. Okay.
No shear and axial force.
The shear force and axial forces are ignored. Ignored. Yes.
Residual stresses are also ignored.
Yeah, that's the main thing. And then the deformations are very small. Yeah, these are the main ones anyway. So throughout everything that we've done so far, the only thing we have been talking about is the moment, bending moment. Yeah, and we said the axial force and the shear are negligible. What I would like to do today is explore the effect of the axial force. So what impact has the axial force on the plastic moment? So if you have a plastic, if you introduce the plastic moment, okay. So what we want is effect of.
It's not clear.
Yeah, it needs. Too big, isn't it? Come on. Is that better? Mm-hmm. Effect of axial force, okay? That's what we want. All right. Okay, let's take a typical beam, let's say, like this. All right. And let's say that the beam is simply supported and we have some uniformly distributed load, okay? And we have some axial, this is the neutral axis here. And let's say we have got some axial force there, okay? And so we say, so what we have here, okay? So what we have a both bending and the axial force acting together. Let's assume that the section is rectangular, solid rectangular, okay, to make things simpler. And your axial force is acting along neutral axis. So if I draw the stress distribution diagram at the different stages, this is the beam cross section. Leave a lot of space here. Okay. So this is the neutral axis. If you want, this is the elastic neutral axis, okay? Then initially we have the bending stress. This is the bending stress. Okay, which is where you have the stress here is actually less than sigma y. Yeah. So initially, when you apply the loading, you've got the stress due to bending. What else have we got? What else? In addition to bending, what else have we got? Okay, you have the axial force. What is the stress diagram where you have an axial force on its own? Triangular, rectangular, what is it? Do you agree it's rectangular? Because the axial force is acting over the entire surface. So you have plus this diagram. This is due to bending. That's the bending stress. And this is due to axial force. Okay, so we have tension at the compression at the top, tension at the bottom, and we have the compression from the axial force. Okay, and we have the combination of the two together. When you combine the two together, what do you get? You get something like this. So what do you get at the top? Compression, yeah, when you combine.
Yeah.
What do you get at the bottom? When you put these two together, do you get a value less than this or bigger?
Less.
Okay, so we have something like this. Yes? Do you agree? Yeah. And this is the combined diagram, okay? This is combined. Okay. So when you combine these two, as I said, you get this diagram here. What happened then if you keep increasing the load? What happened then if you keep increasing the load? Sorry? Yeah, I mean, so when you keep increasing the load, at some point you start getting yielding forming, isn't it? So we start the yielding, we start at the top there, okay? And we have more yielding. I'm jumping the stages, I don't want too many stages. So are we going to have more yielding at the top than bottom, you agree?
Yes.
Okay, so we might have something like this. Yeah? All right, what happened then? If we ultimately, what happened when we get to the end? Do you agree we get this? Something like this. Yeah, it depends on the magnitude of the normal force. But do you agree we get something like this? Yes? When the yielding has spread to the whole section. So so the neutral axis has spread, has shifted. So what is this axis here? This axis, where is it now? Where is this axis? Anyway, so we get a situation where we have this stress distribution diagram, which combines the effects of shear force, axial force and bending together. I should have left more space. I need more space there. So I do it on the next, I do it here, okay, sorry. So this continues, okay, sorry. So what do we do? I mean, what I can do here, this diagram, is equivalent to is that the same? Agreed? Yeah. So this diagram here is equivalent to these two diagrams. Okay, agreed. Now, we have compression at the top. So let's call the compression here C1. So by equilibrium, this will be T1, and they are equal. And let's call the this one here, which is due to the compression, let's call it N. Agreed? Yeah. Now, if you have any questions, just stop me, okay? So do you agree that C1 and T1 are equal and opposite for equilibrium? Yeah. Yes. So we have C1 is equal to T1. What is it equal to? Can you tell me what is? Let's call this this here, let's call it H1. Okay. Let's call the depth of the beam here H. Okay. And the width D. Okay. B, sorry, I'll call it B, sorry, keep it B, okay? So the depth of the beam is H, and the width is B, and we call this part here, we call it H1. Okay, now, can you tell me what is C1 and T1, or T1? What is the, what is it?
B times H minus 2.
It's sigma y, then what?
Sigma y times H over H minus.
Do you agree it's the area of this part here? So if this is the section here, yeah. So we're looking at this area here and this area. You agree? Yeah. So for C1, what is this area here?
H1.
B
H minus
times what?
H minus
H minus
H1 over 2.
H minus H1 over 2. You agree, everyone? Yeah, that's it. Okay. So C or T or T1 is equal to sigma y times the area, which is B times H minus H1 over 2. Okay. What is the moment? Let's call it P dash, okay, to distinguish it from MP. What is the moment due to C1 and T1 because they are equal and opposite? What's the moment? It will be C1 or T1 times this distance. You agree? Let's call it Z here. All right. So C1 sigma y B H minus H1 over 2. What is Z? What is Z? What is Z? How do you work out Z?
It's H.
This one here is H minus H1 over 2, right?
Yeah.
So
if you divide it by 2 again.
No, you don't have to because that bit and that bit, okay, is H.
H
So
minus this one.
So it's H1 plus H minus H1 over 2. Do you agree?
Yeah.
Yes? Okay. Which is when you multiply by 2, you have 2H1 minus H1 is H1 plus H. Do you agree? Yes? So that distance Z is H plus H1 over 2. Okay. Let's test your maths. What is H minus H1 times H plus H1? Do you agree?
Yeah.
Yeah. Over 2 by 2, 4. So it's sigma y B, okay. I'm going to take H square outside. That will give me 1 minus H1 over H squared. Do you agree? Okay. Is that clear? Yeah. So what do we do it now is do you remember this? What's this here? Look at your notes from the first week. What is sigma y? BH squared over 4.
MP.
It's MP. It's MP. It's MP. Yeah. So MP dash is in fact MP times 1 minus H1 over H squared. Okay. Is that clear up to this point? Okay. What is N? What is N? Yeah, what is it? Can you give me the equation? What is N? Remember, force is, stress is force over area. So force is stress times area. So what is it? Sigma y times? What is this area?
H1 into D.
H1
Into
B over 2. That's it. Not over 2, sorry.
not over 2.
Okay, so we have N is sigma y times the area BH1. Is that clear? Do you agree? Yeah, it's N is the stress times the area, which is BH1. Is that okay? We define N0 as sigma y BH as the squash load. This is the axial force acting on the entire section because BH is the entire section. You agree? Yeah. So N0 will be the axial force that acts on the entire section. In other words, this is your N0. Do you understand me? Yes? Yeah.
Can you explain that again?
I said N0 is sigma y times the area BH. BH is this here,
Yeah,
which is
the whole.
the axial force applied to the structure on the entire section. Is that clear? And we call it squash load. Okay?
So if we need to find out the axial force, we
The axial force normally is given. Okay, that's N0. If you know the sigma 1 and you know sigma y and you know B in H, you can determine N0. Okay, because it's the section times the stress, both given. Now we define, let's put N as the ratio of N of an N0. So we put N is N over N0. I mean, this factor is the what we call the squash load factor. We call this the squash load. In other words, it gives us what percentage of N in relation to N0. Okay, so N is sigma y BH1, and N0 is sigma y BH, and you can see that sigma y cancel, B and B cancel, and it's H1 over H. Therefore we have N is n over n0 is h1 over h. If we go back to this equation here, this here, so therefore, MP dash is equal to MP times 1 minus n squared. So this is MP. This MP is the plastic moment without the existence of the axial force. MP dash is the plastic moment of the section by including the effect of the axial force. So what can you say? What can we say? What does the axial force to the plastic moment? What does to it? If MP dash is MP times 1 minus n squared, what does the axial force do to the moment? Reduce it. Do you agree that 1 minus n squared is less than 1? Or at the least equal? Do you agree? It's always going to be less than 1, okay? Because it's the ratio of n over n0, and we know that n is smaller than n0, so it's obviously you get this factor less than 1, okay? So that means that the existence, the presence of the axial force reduces the action of the presence of the compressive. Let's make it specific. Axial force reduces the plastic moment of the section. Reduces the plastic moment of the section, and we can see by a factor 1 minus n squared. This is how much it reduces. So 1 minus n squared could be 0.8, 0.8, 0.7. It all depends on the magnitude of the axial force. Is that okay? Any questions? Now, if you want, I don't know if I've done it here. Maybe I didn't do it. It doesn't matter. You can plot the diagram. If you do MP dash over MP is 1 minus n squared. Yeah, you can plot MP dash over MP versus n. I leave it to you. I didn't do it, but you can guess. What do you think you get? What do you get if it's n squared? What shape? Linear? Sorry? Parabolic, because you got n squared. So if you plot MP over MP dash over MP, you should get a parabolic line. I think I haven't done it, but I think you get something like this. Check it. Okay? So I leave it to you. Take few values and do it for yourself. Okay? Any questions? Any questions at all? Okay. I think I've got an example somewhere. Let me see if I can find it. Any questions at all? So example, let's take an example.
It was coming down.
Sorry?
It was coming like this one. It starts from 0 to graph.
Now, for n equals 0, you get 1. You don't get 0, isn't it?
For n equals to 1, MP over n
Yeah.
is 0.
For n equals to 1.
Yeah, is 0.
Yes, here.
So
Anyway, check it. I didn't do it. For n equals to 1, yeah, you get 0. Okay? And therefore n equals 0,
n equals to
1. Okay? Do it. Okay? Do it. I've given you a hint. I think you should get something like this, I think. Okay, example. Let's take an example. Let's take a section, 80 millimeters by, let's say, 20 millimeters. All right? Let's say we have a UDL. Let's say we have a UDL. And let's say we have an axial force of 40 kilonewtons. Let's say sigma y is given 275.
What's the UDL?
Do we need it?
We don't, but
We don't.
But when we get the question like this, we'll have to find out everything.
It depends on the question. I mean, in this case, you don't need the UDL. Even if I give you UDL, for example, 420 kilonewtons per meter, you don't need it. It depends on the question. Okay. Now, what I want you to do is, using the equations, all of them, can you work out what is the squash load, the squash load factor, what is the reduction, and then give me the answer. I haven't done it, so I want to give you about 10 minutes to do this, please. I just tried to find the example here. Have you got all the data you need? You have? Okay. Because I've got an example somewhere. I just need to find it. Maybe I have the example here. I don't know. Okay, I've got a different example. We can do this.
That's just the age. That's the whole thing. Yeah, it should be like that. That's the tricky part.
Okay, what have you done? Can you tell me what you've done? First of all, can we calculate N0?
Yeah, that's.
Can we calculate N0?
We have.
Yeah, we have sigma y. We have, okay, here, N0 is sigma y BH, isn't it? Yeah? So you can determine N0 because we know sigma y is 275. We know B and H, 20 and 80, okay? So if you do that, please. Okay, so sigma y, N0 will be sigma y times BH, which is 275 times B, 20 times 80. Be careful, always pay attention to the units. What do you get, please? What do you get? This answer will be Newton anyway. So if you want a kilonewton, do 10 to the power minus 3. Simple. So what do you get?
44 into 10 power.
44 kilonewtons.
Yeah.
Thank you. So we got 44 kilonewtons.
What else?
440.
440.
440.
440?
Yes.
Ah, not 44.
440.
440 kilonewton. Thank you. Yeah? You sure, everyone?
Yes.
Thank you. So we got we got N0, isn't it? Carry on. What next? Where do you go from here?
We need. We need H1. When we need H1, that's the
You do it step by step. Look at the equations. Do we know N? Do we know N?
No.
We know N0, 440. Do we know N?
No.
N, capital N.
Capital N. No.
What's this? What's this? That's the compressive force. Yeah? That's given. That's why I said pay attention. Look at the all the parameters, please.
Do we actually need it? I think because we have an N. He asked us for the load factor, this portion factor, that's N over N naught.
So we know N.
We don't.
So we have N equals
N over 8.
40 kilonewtons. We know that, isn't it?
Yes.
Okay, that's given. So what do we go? What do we do now?
N by
N
N
over
naught
N.
is equal to H by H1.
Do we know N is
N
N over?
N naught.
N is
H1 by
40 and 0.
So we don't need the H. That's the whole problem. It was a column.
So what is there therefore? What is 40 over 440? Sorry? 0, 0?
0.09.
0.09. Good. Do you know MP? We can determine MP.
Sigma y bx square by.
Yeah, we can determine MP, don't we? Because MP is sigma y bh square over 4. So just substitute. Yeah. So we have sigma y 275. B is 20. H is 80, so that's 80 squared over 4. If you want it in kilonewton meter, you can do that.
8.8 kilonewton.
It will be 10 to the power minus 6 if you want it kilonewton meter. Okay?
8.8.
8.8 kilonewtons meters. Okay? So this is the plastic moment in kilonewton meters. Then we know everything here. We know N, we know MP, so we can determine MP dash. The moment, therefore MP dash will be 8.8 times 1 minus S square, N is 0.09 squared. And you give me the answer. Eight point 8.72.
Yeah.
So what sort of reduction do we have here? How much reduction do we have?
0.1.
So from 8.8 we got 8.7. So what can we conclude here in this case? That the effect of the axial force is really
0.1.
very, very small. Okay? I'll give you a question. If we increase N to, let's say, 300 kilonewtons, can you work out for me, please, the new reduction in the plastic moment? What do we have? What's going to change? N is going to change, isn't it? Do you agree? N is going to change, so that's 300. And 0 is the same, it's 440. So what's the new value of N?
0.68.
Point
64.
64.
68.
8.
Yeah.
Thank you. So now we can, the new value of MP dash will be, MP is 8.8, 1 minus 0.68 squared, which is?
4.73.
Sorry?
4.73. 4.73.
4.73. Is that everyone? Have you confirmed this? Everyone else, please? 1.1 minus 0.68 squared times 8.8.
4%.
Or what do you conclude here?
Major reduction.
You see what I mean? So it all depends on the axial force. So what we conclude in our case, for plastic analysis to be valid, the axial force has to be within a certain range. If the axial force gets gets large and closer to the squash load, then you start getting into the situation where you cannot ignore the axial force, and you have to include it using this formula for your plastic moment. Is that clear? In our case, when I don't say anything, that means we are ignoring it. Yeah, but in practice, in real life, if you have got a beam where you have axial force, bending, and so on, you need to perform this check to make sure that you are not ignoring that the axial force, you can actually ignore it. I mean, with some judgment, you can see that when it gets close to this, that means you cannot ignore it anymore. Okay, but it shows you that the axial force can have a significant effect, especially in buildings. If you think of a frame building where you have got everything, you haven't got just bending, you've got bending, shear, you've got axial force, etc. Then you need to be careful when you're designing that you are not ignoring something that shouldn't be ignored, because it has an impact, as you can see here.
It majorly reduces the moment.
Yeah, you can see it's almost like a 50% reduction, which is quite significant. You can get away to about 10-15% reduction. That's fine, but when you get to reductions of 30 plus, that's major. That's major. Okay, because that means you are designing your
Overly.
Yeah.
Yeah.
No, your design is not safe. That means your design is not safe. And the good thing is that in practice we use a safety factor to compensate. Yeah, we always multiply by safety factor, but nevertheless, if the axial force is too large, you have to be very careful. Okay. Any questions? I think we finished this. I just wanted to cover this today to give us a little bit of a break from what we've been doing. So next week we go back and we start looking at picture frames again. Okay. And if you have any questions, just keep emailing me. Okay. Is that okay for today? Thank you. So I'm going to stop the recording and I will upload it later. Okay.